In this video, I'm going to show you how to use the ratio test to determine whether a series converges or diverges. This only works on series with positive terms, but if you have negative terms, you can use absolute convergence. What we're going to do is we're going to take the n plus first term of the series, divide it by the nth term of the series, and take the limit as n goes to infinity. What we're doing is we're trying to figure out, as I move from term to term, in the very, very long run, what are the ratios between my terms going to be looking like? If the limit is less than 1, it converges, your series converges. If the limit is greater than 1, your series diverges. But if the limit is equal to 1, you don't know. The test is inconclusive, it doesn't tell you anything. Here's an example to start. I want to decide whether this series converges or diverges. It doesn't really matter what the limits are, except that if they're finite, you're guaranteed it converges. So I want to use the limit test. So I'm going to take the limit as n goes to infinity of my k plus first term divided by my kth term. So for the k plus first term, I'm just going to replace all of my k's with k plus 1's. And notice down here in the denominator, this is 2 times k plus 1. It's a common mistake to think that this is 2k plus 1, but it's actually 2k plus 2. And I divide by my kth term. In order to figure out this limit, I'm going to clean this up a bit. It's usually best if we group the like terms. So I'm going to put those e's together. And I'm going to put those factorials together. Now a lot of things are going to cancel. The e to the k plus 1 divided by e to the k, that's just going to leave me with an e to the first power. These factorials, remember for the top I start at 2k, and then I go down by 1 and multiply all those numbers. On the bottom I start at 2k plus 2. I go down by 1 to get 2k plus 1, down by 1 to get 2k, and so on. And so I see that this whole tail, everything's going to cancel off. And what I'm going to be left with is just those first two terms on the bottom. Now it's pretty easy to see that when k gets real big, this e isn't going to matter, this limit is just going to be 0. So since the limit is equal to 0 and that's less than 1, that means our series is going to converge. Let's do a second example. Suppose I want to use the ratio test to determine whether this series is going to converge or diverge. Again, I'm going to take the limit and let k go to infinity of my k plus first term divided by my kth term. And to find out this limit, it's usually nice to group the terms that are similar. So I'm going to put the 4's together and the other terms together. Now 4 to the k plus 1 over 4 to the k, that leaves me with a 4. And this other piece is k over k plus 1 to the power 5. So as k gets really big, this starts looking more and more like 1. 1 to the power 5 is 1, so this limit is actually going to be 4. And 4 is greater than 1. So we're in this case, the case that my limit is greater than 1. So the ratio test tells me that my series diverges. Let's do a final example. Suppose I want to try the ratio test on this. Again, I set up my limit. And again, I'm going to simplify this to make it easier to calculate. Now, if you're pretty good with these limits, you can already see that what's going on underneath the square root as n gets real big, this is going to look more and more like 1, or the square root of 1, which is 1. And here on this side, this is a rational function, and everybody has the same power. So this limit is also going to be 1. So the whole limit is going to be 1, and this means our test is inconclusive. We need to use a different test. So before we use a different test, I'm going to quickly do a little bit more of a calculation just in case you weren't quite sure why this limit was equal to 1. underneath the square root, this is 1 plus 1 over n. And then up here on the top, if I divide the top and the bottom by the biggest power in the denominator, that's n squared, this often makes it easier for me to see what's going on. N squared divided by n squared is 1. 1 divided by n squared is 1 over n squared. That takes care of the numerator. For the denominator, this is n plus 1 over n squared minus 1 over n squared. Now it makes it a little easier to see what's going on. This 1 over n, this is going to go to 0, 0, and 0. So this piece here really does look like the square root of 1, which is 1. For this piece here, n plus 1 over n, this is also going to go to 1 because it's just the same as what we had underneath that square root. So this here really does look like 1 minus 0 over 1 minus 0, which is equal to 1. So this limit is 1 times 1, which is 1. And this is a problem. That means the test is inconclusive. But it's not a huge problem, it just means we should use a different test. This is a really good candidate for some kind of comparison test because it seems like it's almost like a p-series. So if I want an idea for a comparison, I could say that this looks a lot like this function. Right? That minus 1 probably isn't going to matter much when n is a million. And this is 1 over n to the 2 minus a half, which is 3 halves. And since 3 halves is bigger than 1, by the p-test, this series is going to converge. So now let's see whether we can get away with a direct comparison. If this series converges, in order to do a direct comparison, my series has to be smaller. But unfortunately, it's not smaller. But we can still do a limit comparison. I'm going to take the limit as n goes to infinity of one of these divided by the other one. And it doesn't matter which one goes on top. Now I'll clean this up. And this limit is going to be equal to 1. Now remember, for the limit comparison, things are different than from the ratio test. For the ratio test, 1 is a bad number, it doesn't tell you anything, but for the limit comparison, 1 is fantastic. Any limit that's greater than 0 but not infinite is going to tell you that both series do the same thing. They either both converge or both diverge. So both this guy, 1 over n to the 3 halves, and our original series are going to converge. So the ratio test couldn't tell us anything. We had to use another test, and the other test happens to tell us that this converges.